Hi, my name is Nate Nestler, and we're doing another recording here for Hyperactive Studios, and this is with the series for the CG shading programming. And this is really awesome language. So I was talking about the CG shading programming language from NVIDIA, and the reason why it's so cool is because we can write in one language to go to both DirectX and OpenGL. And DirectX's shading language is HLSL, and then for OpenGL shading language is GLSL. Well, by writing it in this one language, we get both. And the great program for coding this stuff, for the most part, is going to be NVIDIA FX Composer 2.5 at this current time and point. Now, there has been a new release of the CG language 3.0, and the FX Composer 2.5 was for the previous one. And so we don't have some of the new capabilities like tessellation shaders and things of that nature in the FX Composer 2.5. So later, I suspect when NVIDIA releases an update to this program, we'll have that capability. But for the meantime, and for starting out here, it really doesn't matter because we're going to focus more on the standard features that you would see across most cards, because tessellation shaders are only available in the newer graphics cards that have been released by NVIDIA, which is a good reason to go out and get a new card if you don't have a newer card. But for the most part here, we're good for just doing this earlier part of what was done with the shading language, as far as the vertex and fragment shaders in particular. Then we'll move on to geometry shaders later on, and then tessellation shaders. But for now, we're going to focus just on vertex and fragment shaders. Now, we already talked about vertices, and those were basically those points on that model when we were manipulating them inside of Blender earlier. And fragment is basically an unprocessed pixel, if you will. And that's what they're talking about, fragments. So each fragment is literally a pixel, if you will. Well, feature pixel, if you will. And so when you hear people talk about fragments, just think of it as being pixels to be computed, more or less. Alright. And with that in mind, let's have a look at some of the capabilities and features of FX Composer. Now, there is another program that's really awesome, and it's used quite often in the game development, and that is Mental Mill. Now, Mental Mill is from Mental Images. These are the same people who do Mental Ray. It was done on a whole bunch of films, such as The Matrix is a good example, but many other films too. It's including some films people will probably be so shocked to find out that there was actually 3D effects in the films. However, this was a really good top high-level language, and they've created a real-time shading environment that works for CG shading and also HLSL and also GLSL. And the cool part about it is that you can graphically node-based, as it's sometimes referred to as node-based programming, you can graphically connect up the nodes in order to generate the code for HLSL or GLSL or CG. And as we say in the game and film industry, there's no such thing as cheating. It's just get it done and get it done quick. So if you feel like it's cheating, it's not cheating. Trust me, it's not. When you get the code back, it's a real quick way of prototyping something. So instead of spending a lot of time trying to create some shader effect, maybe you only spend a few minutes, or maybe an hour or something like that to kick it out. And then you can sit there and have a prototype working there to test it and test out ideas very quickly and very fast. Because all you have to do is graphically hook up node connectors to it, and then you can, reasonably get a look that you would like. I'll show that off later on at a later point in time, Mental Mill, but it's very powerful. And what's so good about that is it would take a lot longer to hand edit code in order to get those same kind of ideas tried out. And in this way you can get an idea quickly kicked out and tested. So the other important aspect of this is that once it generates the code, you're like, oh, I'm done. No, you're not done. You've just got a nice prototype set of code. It may not be optimized to the same level as what you would need, and especially in a production environment. So now that you have working code, so now this basically lets you kick out working code quickly, but then you need to go in and enhance it to be faster. Maybe some methods here or there where you can take out stuff or rearrange things where it would be more optimized and run a lot faster by doing it that way. So it's by no means an end-all solution here for this stuff, but what it is a time saver, and it is a nice little production method to quickly prototype and kick out an idea very fast. It used to have Mental Mill as part of FX Composer back when, and it was free for a while there, but now it's $500 for a copy of it, and you can have it either on Windows or Linux. So It's a great tool, and it's certainly a wonderful method of doing this stuff. So I encourage you, if you have the money, please go check that out, because that is a very powerful program, and it's great. It's at middleimages.com. So, but for now, let's have a look here at NVIDIA FX Composer 2.5. Okay, so one of the awesome aspects here is they got a video overview, which will help give you an idea of how to go about doing some of this stuff. It's a little bit different than maybe what you have set up already. They also have a quick tutorial and a user guide, which is very useful. And then we have a new project and an open project. Now, if I click on new project, it's going to let me start a new project. So, you don't know. Then you put in the name of it. So, for instance, I don't know. How about just test project? I don't know. Not a very good name, not all that descriptive, but all right, fine. It'll work for now. Click OK. If I'm doing an actual effect or an actual shader or something of that nature, I'm really going to want to name it properly, and that's very important. Okay, so let's point out a few aspects here. Here's our 3D render view here, and you're like, well, no, cool, but I don't see anything there. Well, no problem. If you want to create a model in here from one of the defaults here, we have one, sorry, pre-programmed sphere, a teapot, a torus, or a plane. Sometimes here, where did the teapot come from? A teapot's nothing more than a test model, just like the Stanford Bunny is, or some of the other models that are out there. Torus, same thing. You know, you might use a torus in real situations. A teapot in model, never use this from a base. These other ones here are primitives which artists can use to make things with. Usually a box is quite popular too. Also, something else important to note. We can change between DirectX, viewing this system in DirectX or OpenGL. I'm going to stick with OpenGL for now. But since we are doing CG programming, again, we cannot have it execute both in DirectX and OpenGL. So this way you can test your shader to make sure it's working properly in both. Now it should just automatically compile down in both, no problem, and work well, but it's always good to test. Also, there's a performance analyzer, which we'll get into later on here. It also has Python scripting in it. We have tasks here, output, and a texture list here. If you need to pull up any views that are missing, it's no problem. Just go over here to the view panel here, and then you can select different ones to make them appear. And that's very cool. And very, very useful. And here's the editor for the shader. Now, that's not really appearing for anything right now. It's because we don't have a shader. And right now I have a shader library here, which I can select different shaders that are up on NVIDIA on the web, and by selecting these, it'll automatically download and put them in here. And I can choose CG or HLSL. Now remember, HLSL is DirectX, or if there's a collada one, I can select that, or a video, or a white paper, or a download, or whatever, if it's available. Only if it's available, of course. And you'll see a host of techniques, and relief mappings is always really awesome. But there's a host of different techniques here that you can make use of, and from different standpoints and such. But we'll be going through some of the math, what's involved, why things work the way they are, breaking things down, and making it to where it's easier to understand what on earth is going on here. You see some very cool effects like this, image post-processing glow here, or you saw the crepuscular rays, or sometimes referred to as God rays, in here too. And there's just a whole number of features. You can also animate these shaders, do all kinds of crazy things with them. It's very cool and very powerful, and it really allows you to add a whole lot of extra effects. So here's a material for environment, classic bump, textured, just lighting, animation, DirectX. You can also do bone animation through shaders for the skin, doing the skin through a shader. There's a bunch of stuff. Here's image processing glow texture, which is always nice. Here's another image processing glow here too. It's just a whole lot of really neat things. Post frost fast here, etc., etc., etc. Different techniques and different methods for doing things. And there may be more than one way you would want to do something, and particularly you would do that due to speed. Maybe anytime you can do screen space type operations, it's much faster. Here we got some kind of stylized skin shader here. I don't know if it's actual, it's Lambert skin. It's not like an actual SSS skin with subsurface scattering skin. We'll get into that later on. But basically, if you have a screen space technique here, that means you would actually render the effect in the actual screen itself and not necessarily the objects. and so you don't have to have a shader per object, meaning you could have, like, I don't know, 10,000 models, floating around here, right? And you just do the screen space shading for the entire screen all at once. So you only have to have one shader to handle the whole screen. Great, awesome. And that makes it very fast, as opposed to having 10,000 shaders going on for those other models in order to get the same effect. So you can see why screen space is so fast. That's why it's okay to have multi-pass shading for screen space typically. And you wouldn't want multi-pass shading for individual shaders, because if you had 10,000 models, right, and you had multi-pass shading for 10,000 objects, that's going to get to be insane. It wouldn't just be 10,000 shader passes you would have to do. Say it was 2-pass, right? It didn't be 20,000, because that means it has to do 2 passes of computation per model per shader, and then that's going to get to be very intensive, right? Say if you have 5 passes or 6 passes, now it's gotten even worse. You're talking 60,000 passes. That's nuts, and so it just gets exponentially crazier. But you can see why on the screen space is not a big deal. Say you have 5 or 6 on the screen, it's just 5 or 6. That's it, because it just takes up the space of the screen. So that's not a bad deal. So you have to be careful when you're talking about doing for an individual model here, which we're going to be messing with earlier on here. You definitely want to try to stick to the single pass. And what I mean by single pass is this is the amount of execution statements you can do in a single execution cycle on the 3D card, meaning you don't have to go back and do a whole nother set of processing steps later on to do another stage and then yet another stage and so on and so forth, because each stage would be another pass, which would be a whole nother set of calculations. You want to be able to do it all in one calculation time frame, so that way you can do it per frame much faster. Let's just have a faster frame rate. Now on games, you're talking about doing interactive games, it really needs to be about 60 frames per second. That's pretty much the standard in games, and you really want to hit that. And the reason why is because it makes it really feel like it's interactive when you do that. You get a better response time to your button clicks and things like this, and so it makes the game a lot more fun or exciting to play. When you don't have a very responsive game, then people get upset and frustrated. So your responsiveness is the most important, and then everything else falls down from there. Graphics are always very important for games typically, along with gameplay is super important too, and if not more important a lot of times. Okay, because you can have a beautiful game, but if it's not fun to play, then what's the point? Yeah, tune shading, and we'll get into a number of shading and techniques and the different effects and things and where it comes from and the mathematics behind some of the stuff and whatnot, and we'll get into all that. But here's a whole list of potential shaders that are just right there, ready to go for you to play with. Very nice. Okay, so here's where you can load your models. You're like, okay, well, you said you can load these models here. Yes, but you can also load other models that are of art style and everything, and we'll play around with that. I'll include one of my models that I've done with this set of videos for you to play with, so that way, you're not sitting there with nothing to work with. Unless you're an artist, you're probably not going to have access to it. And I'll also give you resources too, where you can get a whole bunch of free models that you can then import into here, no problem, and have access to. But you'll see this OBJ here. You can import OBJ. You can import Collada. Now I've talked about some of these. Here's your FBX format I was talking about. 3ds is used sometimes too, and it's hard to get good standards on 3ds, I think, in the most part. And then also DirectX file format too is available. But if you were to have a model in here that you could load in here, which I actually do on my computer, but I'm not going to bother hunting one down right now, then you can load it up in this view here, and then you could see it. Oh, well, maybe I will. Don't want to not show you, I guess. Oh, wait, no, I don't have them on this machine right now. Okay, so I will show that later on. Okay, so it's on my other computer. Okay, so we have different models here. Let me just real quickly create a model so we have something to work with for our shader. And bam, there's our model. So here's our teapot. And if I hold down Alt and right click, I can move my viewport around to rotate, dolly, pan it, etc. Zoom in and out. If I use my mouse wheel, I can zoom in and out. And I can click on it with the left click to select my model. Right click lets me bring up a pop-up menu here where I can do all kinds of other things. And then if I hold Control and left click, check it out, I can pan versus dolly versus zoom. Okay, and I'm just going to zoom out a bit because that's getting a little too close to me for my taste here on this. Okay, so very cool. Now, if we're wanting to have a new shader, we want to code, we need to do an effect. All right, and the effect we're going to want to do in this particular case is just going to be a very basic shader. So let's have a look at that real quick. Well, no, I'll tell you what. Let's show off some stuff really quick. Sorry. I do want to show off some other capabilities you can have. You can also have effects here. So say I do fire here, and I click it, and if I hit play, it will actually play back this fire effect on the shader. And now the teapot is burning with fire. So yeah, we can actually do fire, all kinds of particle effects, and all manner of things in here. And Collada has a very cool format, the FX format, and you can basically encompass models, shading textures, you name it, all into this format to make it portable between different environments, different programming programs that can then read in the FX format, and you would need to be able to read in the FX format. And that's really great because it really makes it easier to transport all the stuff you need, including animation. And as you can see, this is animated. In addition to that, the other aspect that the CG language has in it that's really awesome and makes it so great is that you have shader profiles, and this gets into, well, say that you have newer hardware and it's capable of doing some more effects that older hardware can't do, and so you want to make it look as good as possible on the people who have the newer hardware and not, basically penalize them for having newer hardware. But at the same time, you don't want to cut out your customers that have lower end hardware, because if you cut out your customers that have lower end hardware and they don't have the money to go out and buy the new hardware, you just basically lost money. And if it becomes significant, well, I guess, case in point, Crisis. There's a good example of when the game was released, it looked beautiful, but hardly anybody had the hardware capabilities that were required to play the game. And so there's a good example of that, where you have to, account for people having lesser hardware and greater hardware, and so this shading language lets you code out for multiple target points for the hardware profiles, and then in this way you can have greater and greater quality shaders, or lesser and quality shaders, depending on the hardware and what it can handle. And so you can basically optimize and tweak for different hardware too. So this is really nice, and it really makes it where it's more portable. You get better results. You can also pre-compile shaders. You can also compile the shaders on the fly during runtime. So basically meaning you can have the shader already compiled. Like maybe we saw some of the earlier games where they were loading up, it said loading, compiling shaders, whatever. It'd only do it for the very first time you run the game, but it'd have to compile all the shaders when you first pull up the game. Well, you can get around that, now, because they have compiled shaders as part of CG language, and so you can already have this pre-compiled shader that when the game just loads up, it's already compiled and it just plays right away. You don't have to wait for it to compile the shaders. So of course this has definitely some nice effects to it. On the downside, you're not compiling the shaders specifically for that particular hardware of that user, so maybe you don't get the best acceleration, but who knows, maybe you do, depending on how it compiles down. But so here's this fire effect. Alright, I'm going to go ahead and stop this real quick, and that's all I have to do to stop it. I'm just going to hit Control Z, lets me undo, and lets me go back. Let me try another one here. So I'm going to show off another one. To overwrite this file, sure, whatever. Yep. And so here I'm bringing this one back here. Okay, again, let me hit play. And it didn't quite take, so let me hit play again. And there's your fireworks. And so you can see a fireworks particle effect. And, there are some really good methods for this, for how to go about doing this. This is really just an image that's facing towards the camera at all times, and then we can sit there and multiply some mathematics to colorize the different ones and make them fade out, and over the life of the particle and all this stuff. We'll get into that later on eventually. But for right now, it's showing off some of the capabilities you can do. So you can do a lot more than just make a pretty skin on top of a model or something of this nature. You can actually do effects and animations and just all kinds of crazy awesome stuff. So let's have another look here. See if we can't get to play nice with this. Alright. And this is smoke here, and it's smoky. It's okay. It's not like amazing or anything like that. It's not pyroclastic clouds or anything like that, but it's not bad. There's ways of doing that kind of stuff, and you can do it volumetrically and everything, make it really nice. Smoke effects and things of that nature, but usually effects take a backseat to everything else, unfortunately, for most games, because it's just not as important for the explosion to look as awesome as it is for character animation or shading, or some of that stuff. It just ends up taking precedence over the environment looking amazing at all times. The effects usually take a back seat, unfortunately. On some of the film-based programs, they actually use node-based. For the more advanced ones, for the effects, they use a node-based method for doing. Let's talk about that node-based programming for connecting up these. Basically little graphical nodes you hook together in order to generate the particles to create these effects and stuff like that. And each one's like a little mini function or program that you hook to another one to drive the effects and stuff, and then an artist can use this to do all kinds of crazy things, which is pretty powerful, and it's a pretty nice setup. But again, you don't typically see that on games, unfortunately, for now. That might change in the future. We'll see what happens. Okay, so here I'm just going to pull up the teapot again, and I'm going to create effect. So I'm going to do this effect here. I'm going to choose my CGFX, and I'm going to say next. And I could say HLSL if I wanted to have HLSL too and do both of them at the same time, or Claude FX, CG, whatever. For right now, I'm just worried about CGFX. That's all I'm concerned about. We have a lot of different choices here. And this is just basically like a basic shader to get you started in a certain direction you want to go, so that you're not rewriting everything from scratch. So it's great. So this lets you basically think of it as like a launching point, so that way you're not starting from scratch. It makes so much sense, so much more sense to start from a nice basic base point, than starting from scratch to get something done. And it makes a whole lot of sense. So that's what we're going to do here. But in this case, we're going to say empty, and I don't know, I'll call it like very simple shader, perhaps. Alright, so a very simple shader it is. So I'm going to say next now. And it's going to go ahead and put this in for the name for the material. And then for an effect, you can have multiple materials for an effect. It's fine, but you need at least an effect for something at least. Can't go along without nothing at all. Alright, and so here's our actual shader here. And this is the code for it. You're probably going, this doesn't make any sense. Don't worry, I'm going to go over the language here. Over here we have our parameters here for modifying the stuff over here. Now you see something right now. Model, view, projection, right? Because this is our model view matrix with our projection, coordinates for doing the distortion as it gets closer to the screen. As you can see, it's happening right here. See how this thing gets bigger as it gets closer to the screen versus the part away from the screen smaller. So again, that's your perspective distortion, and that's what that is. So remember that crazy matrix C mathematics we were talking about in the last two videos before this. All that makes up this one little variable right here when it's running through the card, and so that's what that is, where it's coming from. Now, if I just left drag my shader on here, I can just drag and drop it directly right onto my model, and poof. You're like, well, that looks terrible. Yeah, well, we're working with a very basic shader right now. So in order to keep life simple, when we're first starting out here, is we're just going to work with a very basic code, and we're not going to, we're going to take it baby step by baby step. So we're not going to go crazy over this stuff right now. Okay, so this is just the most basic of basic shaders right now, and this is basically we're kind of simulating a fixed function pipeline in this way. It is so simple, we're just not hardly doing anything practically. Here we got a float 4x4, and this is a 4x4 matrix, and it's a floating point. So each variable, so if you were to multiply this out, this is going to be 16 variables, right? Because 4 times 4 is 16. So that means you're going to have 4 variables going across, and then 4 variables going down. You know what I mean? So we have 4 variables here, 4 variables here, 4 variables here, 4 variables here, and a table, more or less. And that makes up your matrix. And if you went through the Matrix Math series, then you'll totally understand what I'm talking about right now. If you haven't, then you really need to check that out and go ahead and purchase that so that you have an understanding of it. If you already know Matrix Math because you took a course on it or whatever, then this is just old hat for you. Great. But if not, then you really need to check that out. Otherwise, you're going to be very lost. Float 4 here. This is going to be a vector, and this is basically like your XYZW type setup here. And then we have our position here, and we named this function. All right, so we got a function name here, and it's main VS, and this stands for the V and S. Now, this is not required. You can name this anything. You can call it, I don't know, purple polka dotted thing or whatever. You know, it doesn't matter. But you have the main here, VS, for Vertex Shader here, and this is because we're working with the vertex. Now, in the pipeline, when you're getting to doing these shading methods or whatever, you have to do vertex before you do fragment if you're going to have a vertex shader. It always has to go in that order. I'm like, well, why does that matter? Well, the reason why it matters like that is because you always have to have the geometry in order to apply a texture or material to the geometry, right? And so that gets into the vertex. You have to have the position of the points on the model in order to actually apply a skin, if you will, or a shader or an effect across that model. So if you don't have those points in those positions, you can't do it. It's impossible. Now, you can't actually have a fragment shader without having a vertex shader. And you can have a vertex shader without having a fragment shader. Remember, a fragment shader is going to be a pixel shader. Sometimes it's referred to as a pixel shader. And that's what the PS here is for. So we have a float 4 here, main PS. And it's not like, you know, PS, how you doing, wherever in the bottom of the letter. No, what we're talking about here is pixel shader here. So we're in main PS. Now, you don't have to name it this. Again, purple polka dotted purple person eater or something like that. I don't know, dude. We have open close parentheses here and colon and then color, and we've got color going on here with this, and we're doing a open bracket here to starting, and then a closing bracket ends a function statement. And so this is the return type here. This is a float 4, and it's a vector for float, so XYZW. And that's precisely what's getting changed here. In this case, we're talking about RGBA, because it could be XYZW. If you're talking about position, if you're talking about color, it'd be RGBA. You know, and so that gets into color for each one. So if you had a channel here for each one of these, floats more or less, and you have a range of color based on the floating point of the graphics card for what's available with your float. And you can also have a half, and we'll get into that later. Well, I'll just say it right now. Half is a half float. So it's half the precision level of a float. So it lets you take up less space than what you would have with a float, you know, variable in memory. And so it lets you have lower quality color on some things, but if it doesn't matter and you can squeeze it in, then that means you can do a lot more on the card because you have more room for doing things than you would have otherwise. So if you don't need that extra precision or whatnot for your color, then it makes a whole lot of sense to use half for different places because you're going to get speed acceleration by doing so over the float. Okay, so in this case we have, you know, the first number is going to be R, which stands for red. So RGB, red, green, blue, alpha. Alpha is going to be your transparency. So as you probably imagine, this is red, so the next one has to be RG, which means green, right? So the next one's green. Goes from 0 to 1. And you can have overly bright colors if you go into high dynamic range, but for the most part, if you stick between 0 and 1, and there's some mathematics tricks, by the way, you can do too, going with the 0 to 1 range for like inversing colors and all this crazy stuff. It's awesome, which we'll get into later on for doing some math with color. But basically, I take this number here, and I do 1.0 here, then this is going to be full red. This right here is full green, and then this right here is going to be full blue with a 1.0. And then full alpha means totally opaque. Now if I had this as a 0, it'd be totally transparent. I wouldn't see anything at all. 0.5 would be half transparent, half opaque, you know, so it'd be like semi-transparent, if you will. Of course I can run that number up and down for point precision anywhere from 0 to 1.0 here. So this is very cool and very powerful. Now this is additive. This is light. Because we do have light emitting from the screens, we're working with an additive system and not a subtractive color system. Subtractive color system may be paint, for instance. So you put paint on a wall, that's a subtractive color. You take all the paint, you mix it together, you get black, right? And white is the absence of color in a subtractive system. In the case of light, it's the opposite because it's an additive system. So if you add all the colors together in light additive system, then you get white. the absent, and this makes sense. You're like, well, that doesn't make sense. Hold on a second. It makes sense if you think about it. Because if you have no light, you have black. That's it. So black is the absence of light. That's how it works. So that's why they talk about additive and subtractive systems, two different things. This is why it gets kind of tricky when you go from an additive to a subtractive system. Think about this. If you're trying to print the colors that are on the screen to paper, the screen is additive, but the paper for the printing is subtractive, right? Because you have your CYMK. Oh, wait, totally different color system, right? Yes, totally different color system because it's subtractive, and then the color system for the computer screen here is additive, and there's always a trick for making those match up as close as possible, including calibration of the screens and all that. Thankfully for 3D graphics, we really don't hardly have to ever worry about that kind of stuff unless you, for some reason, have to print 3D models. I don't know. It's not something that really hardly ever comes up. For the most part, for your games, you're just really worried about running around playing games. But I use that as a point of pointing out how these systems work and what we're doing. I'll prove this to you. Oh yes, it's not just a bunch of words. We're going to prove it. So say I want to make this teapot red, right? So that would make sense. I would just say 1 here for red. I would say no green and no blue, and I want it to be totally opaque, so there would be 1.0, right? So this would be 1.0 for full solid red. And let's have a look over here. We're going to have to pass through our position of our points. So we're passing in position to be processed, then to be returned out. And so that's what the float 3 here is, XYZ, being passed in. And we're going to multiply our position times our world view projection or model view matrix. And what this is going to do, of course, is give you the screen space distortion for it. And we end up with, coming back with typically clip coordinates here. So float 4, we have our pose.xyz here for position, and then 1.0 for our W. Now remember, we're talking about non-homogeneous and homogeneous coordinate systems, so we need to make it homogeneous. So we're going to put a 1 in here so that we preserve the magnitude of x, y, and z for the positions. And that's important because we don't want to shrink, if you will, the model. Okay, so by multiplying this through here, and then we have the return type. When it returns, you're like, okay, cool. Where does it return to? Well, what happens is the data from the model gets passed into the Vertex Shader from the program, and that's what's going on. This is how this position is getting here. So it's working with OpenGL or DirectX, right? And it's passing in the positions of the points into the Vertex Shader. And in this case, we're not doing anything other than multiplying the world view projection or model view matrix times, you know, our positions of our points in order to warp them and set them up for the screen space to be displayed properly. Okay, cool. So we do that, and when we return it, it then gets passed to the fragment shader or pixel shader, as you want to call it. So here we have our fragment shader, and it's getting passed in to that in order to be applied to the positions. Really not much to do here. We're only interested in the color for the most part. So here we're applying a color, and then we're returning the color from here. And right now, before I modified this, it was white. You're probably going, well, why is it still white? You just changed the number in here. Well, it doesn't compile automatically. And that's a good thing, because if this thing had to compile constantly as you made every little change, it'd take forever to edit a shader file, right? It'd be a pain in the butt. So instead what it does is it only updates when you tell it to. So that makes it a lot more sense. And that's what's going on here. And I'll prove that real quick. Okay, rebuild all. And bam, and now the teapot is red. See? Red. Now it's red. It's full solid, straight up red, all the way. Now, again, in order to talk about overly brightening effects, well, it doesn't hardly show up on here, but I could do it the other way around. And there we go, half red. So now it becomes a lot darker, right? Say I want it to be green, just to prove a point here. Becomes green, as you would imagine. And yes, that will also become blue, just as, like I said, it is RGB. Okay, very cool. And I'm just going to go back to red, because, I don't know, green's not bad. By the way, green is the strongest color artistically by far on the icons of someone's eyes. Red is the second strongest, and it's by like a magnitude of 10 times stronger green is than red. I know that might shock you, because a lot of people are going to think that red is the brightest color and the strongest color on people's eyes. It's not. Green is by far. And then going down from red, the next color down from red is about 1/10 the power of red is as far as intensity. So I mean, green for the next color after red is 100 times pretty much more powerful than the next color. It's extremely strong color. So be careful you don't have like a ton of green sitting there for a long time on the screen, because you could actually cause people's eyes to have ghosting images when they look away from the screen and all this stuff. It's going to have a very strong effect on people. It's kind of crazy that green is, it's not something you would think of. You just, I don't know, it seems like you think of red being the strongest color, but it's not. Technique here. And it's just automatically labeled a technique. Now we can rename this, however. And then we have pass 0 because this is the first pass. And of course we can rename the pass too. No problem. Cull face enabled can be set to false, so we can turn that to true if we want to cull our faces. Vertex Program, we're going to compile our Vertex Program, VP40. So this is the VP40 profile. Now we can have multiple profiles. We're compiling different shader types here. It's different methods here for different profiles for the graphics cards. Then remember a second ago I said that there were different profiles for different graphics cards, and this is what I was talking about here. And this is a Vertex program here, and this is for the 4.0 for the that particular subset of 3D cards that's used for compiling all this stuff and computing it. So this is some of the newer cards here. So we have a VP40, there's a VP30, and there's a, well, we'll go through it. There's a number of them. But for the meantime, let's just have a look at, this is just one method here. And then what we're going to process main VS, right? Because main VS is this function here. And so we're going to use this for passing to our Vertex program to compile that shader. It's going to compile this Vertex program, and then it'll be passed over to a linking program. It's going to link these programs together for us in real time. You're not seeing that here, but if you were going to OpenGL with GLSL, it has a whole set of steps for a linking process. This is actually quite simplified. It might sound complex right now, but this is actually very easy compared to what you have to do in OpenGL if you're doing it in C++ for actually making all these parts compile. Fragment program, again, remember fragment stands for pixel, uncomputed pixel. So this is our fragment program, and we'll compile our fragment program shader here. And again, it's going to be a 4.0 here for that same kind of format for compatibility, and main PS. Now honestly, since this shader is so unbelievably simple, you could go back to the oldest hardware possible, and this one would run on just everything pretty much, even the probably Intel integrated. if it can even read the GLSL. But I mean, the shader itself is super duper simple, and it will work with just about everything you can imagine. This actual real 3D card. Okay, and so that's basically what's used in order to process these to then be applied to our model here. And that's a nice overview of the most basic shader possible, pretty much on here. Now we cannot artistically change any of these values or these attributes here. That would be nice, and we'll look into how to do that later here in the next video, for how can we make it to where someone can actually edit these values interactively from an artist standpoint and not just from a programming standpoint. Because let's face it, you're not going to want to do a game like this where you have to go in and literally hand edit the code in order to change the color of some model. That's insane. You need to have artistic controls for artists. Remember, you're always trying to facilitate the artists by giving them the best tools possible and make it as easy as possible to do their job, because they have to turn out pretty much like Michelangelo type artwork out of the tools that you make for them. So if you make them tools that are very difficult to work with, you just made their life so much harder. It's not funny. And yeah, you commence to spitball throwing at you, and be prepared for all number of things. Mostly people complain that your stuff is extremely difficult to use. So please be aware of that. And it always does matter very much that you make it the life of the artist as easy as possible, because the harder you make that, it's usually a lot fewer programmers than are artists. And so if you make a tool and it impacts many people, then the cost of production just went up pretty much if you wrote a tool that's difficult to work with, because it's going to take that many more man hours for each person to do what they need to do for their job with what you created for them. So always think towards, is this thing I'm making, is it going to be easy for the artist to use? Is it going to be, are they going to be able to use this to do what they need to do for their shading or their artistic endeavors or whatever they're going to be doing with the models, or am I going to be limiting them from doing what they need to do? Is there a way that I could open this up without really hurting performance hardly? Anything you can do in order to make that better is definitely desired. All right, so let's enough of that, and let's go on to the next video. And again, I'm Nate Nestler, and this is for Hyperactive Studios. Thank you very much.